Okay, so in this chapter, we'll talk about Newton's laws of motion. Okay. Till now, what we have done is described motion. What did that mean? And that subject was called kinematics. What did describing motion mean?
Place relative to time.
Right, so its position relative to time is what you were asking for. Okay? And once you gave that, you could calculate the velocity and from there calculate acceleration. Okay? So you could calculate the acceleration of the object. Now we're going to talk about what causes acceleration. And you all know this. What causes acceleration? Forces. Okay? So that's Newton's second law. So this subject is called dynamics. Okay, so and this was called kinematics. Just terms, don't worry about it. Okay, so this is the most important equation that you need to know. Okay. So, and Mr. Newton figured this out. All right, so that's what this chapter is about. I'll let you guys read all of that. Okay, so Newton was around 1642 to 1725, okay, about 300 years ago. Okay, he was alive about 300 years ago. So his Naturalis Principia Mathematica was published in 1690, okay, and that was the main document. He proposed the laws of motion still used today, and the motion of macroscopic objects. What do we mean by that? Motion of macroscopic objects. I'm sorry? Large objects. So his laws can describe motions of rockets, planets, cars, and stuff like that. His laws cannot describe the motion of what? Atoms, okay? Electrons around nuclei and stuff like that. Yes, for that you need quantum mechanics. So this is his laws describe motion of macroscopic objects. He also discovered the law of gravity, invented calculus, and made great contributions to the theories of light and color. So he did many good things, many awesome things, spectacular things. Yeah. All right, let's come back to that in a second. We'll talk about Newton's second law. Okay, so Mr. Newton figured out that if you apply to get an acceleration, to make an object accelerate, you have to apply a force. Okay, and the proportionality constant was the mass of the object. So what he's saying is, if you apply this much force, the greater the mass, the smaller the acceleration of the object. Okay. So mass is like it resists acceleration. And what is acceleration? Acceleration is change in motion, change in your velocity. Okay. So this is Newton's second law. So force is mass times acceleration. Now again, this is the vector equation. You saw that in mathematics, if you have a vector here, you need to have a vector on the right hand side, and this is a scalar times a vector, the scalar being the mass. Okay, so this is Newton's second law. Okay, now Newton's first law is just a special case, okay, of this equation. If the force acting on the object is zero, if this is zero, what is the acceleration? Zero. If the acceleration is zero, what does that mean? I'm sorry? What? Velocity is constant. Mm-hmm. And that's Newton's first law. So it's really a special case of Newton's second law. And in fact, Mr. Galileo discovered this law. Okay? But instead of calling Galileo's law, we call it Newton's first law because it's a special case of the second law. Okay. Okay, so Newton's first law states that when net force acting on the object is zero, its velocity is constant. Does that mean it's at rest? I'm sorry? No, it's just constant. It's not changing. If it's non-zero, it'll remain zero. I mean, if it's non-zero, it'll remain non-zero and constant. Okay. So, for instance, you experience this for brief periods of time. You played air hockey, and when you get the puck going, it'll maintain a constant velocity till it collides with the sides of the table. Okay. All right. So the SI units for this is measured in kilograms, and that's meters per second. And this combination of units is called a Newton in honor of Newton. Okay. So again, like I said, these combination of basic units are given names of scientists who worked in those areas. Okay. Now this is really a vector equation. What this equation is telling you is that this vector is equal to that vector. When are two vectors equal to each other? When their components are equal. So what that means is the x component of the force is equal to m times ax, Fy equal to m times ay, Fz equal to m times az. So this equation is really three equations. Okay? Or if you were in n dimensions, that would be n equations. Okay? So it depends on how many dimensions you are in. Okay. Now here's another thing I want you to notice about this. See, if you apply a force in the x direction, you only affect motion in the x direction. A force applied in the x direction will not affect the motion in the y and z direction. So this was the reason why when we started off with studying one-dimensional motion, because a motion in a given direction is independent of the motion in other perpendicular directions. Okay? So you apply force in the x direction, you can only affect motion in the x direction. Okay? Did you guys understand that? Newton's third law says the following. Okay, essentially it says, okay, so this person is pushing on the wall. Why did this person go forward? What? Huh?
The wall exerted equal amount of
That's right. Okay, so for every action, there's an equal and opposite reaction. Okay, so essentially, Mr. Newton is saying that you can never have an odd number of forces. Forces always come in even numbers. So you apply a force, you get a reaction force. Okay. Notice, action and reaction are acting on two different objects. Yep. So, for instance, here's an interesting thought. Yeah. So this is the Earth. That's me. Let's say the Earth is pulling me down with a force of 160 pounds. What am I doing? I'm pulling Earth with a force of 160 pounds. Okay. All right. All right, so Newton's third law is for every action, there's an equal and opposite reaction. Okay? So we've already introduced mass. We introduced mass in this equation. And so mass is a measure of an object's resistance to change in its motion. Change in motion is measured by acceleration. Okay? So larger the mass, for a given force, larger the mass, smaller the acceleration. Okay? Now, of course, mass we know is how much stuff you have. The more stuff you have, the harder it is to accelerate you. Okay? So greater the mass of the object, smaller its acceleration under a given force. Mass is a scalar, as you can see from this equation. This is a vector, and you can only multiply a scalar to a vector to get a vector. Okay? That's not true. You could multiply a second order tensor, but we won't get into that. All right. So that's right. Greater the mass, smaller your acceleration. Okay. Now the reason I put this picture is your mass is the same on Earth and on the moon. Your weight is the force with which this object is pulling you down. The greater the, you learn in chapter 13, the greater the mass of this guy, the harder he'll pull you down. So the weight of an object can change, the mass of the object does not change. Okay? Did you guys understand that? Okay. Forces are vectors. Okay. Okay. So what the superposition principle says is the following. Okay. So let's say here's an object. There are multiple forces acting on the object. So the question is, which way does this object move? So what the superposition principle says is the following. Here's this force, add the two vectors, there's a resultant force. Okay? So here's this object, you can apply these two forces, or you can apply this single force, which is the sum of these two forces, F1 and F2. Okay? And the motion of this object would be identical. Okay? So the motion, so when several forces act on a body, the effect is the same of that of a single resultant force. So if you're looking at just the motion of this object, you can't tell if there's this single force acting on it, or is a million forces whose sum is equal to that acting on it. Okay? That's the superposition principle. The force acting on an object of mass 1 kg. Okay, so here we are defining the Newton. The force acting on an object of mass 1 kg, if this mass is 1 kg, is 1 Newton when its acceleration is 1 meters per second square. On 1 kg, if you give it an acceleration of 1 meters per second square, you have applied a force of 1 Newton. Okay. You guys understanding this? All right. Gravitational force, we'll learn more about this in chapter 13. But what Mr. Newton found was every mass attracts every other mass. And the force of gravity is given by this equation. A universal gravitational constant. The gravitational constant is the same whether it's two amoebas attracting each other or two planets attracting each other. Okay. Mass of one times mass of the other divided by r squared. R is the distance from the center of mass to the center of mass. So this object is attracting this object with that force. What is this guy doing? How large is this force? How large of a force does this guy exert on him? You should know the answer. Equal force. Equal, okay. So if this guy is pulling him with a force of 100 pounds, that guy is pulling him with a force of 100 pounds. That's Newton's third law. Okay. Okay, so here is the Earth. Let's say here you are. What is the Earth doing to you? It's pulling you down. What is the direction of the force? The direction of the force is towards the center of the Earth. Okay? And this is the gravitational force. The magnitude of this force is called your weight. You know the direction is toward the center of the Earth. Okay? All right. So G is the acceleration due to gravity that's on the surface. Okay. Any questions? You guys understanding? Okay, so here's this person holding this laptop. Okay, the earth is pulling it down with that force. And since it's not falling, well, let's use Newton's second law. What is the acceleration of this guy? 0. So the net force on it must be 0. Well, this force is acting, so there must be an equal and opposite force acting on this guy in that direction. Well, what is exerting this force? The hand is exerting that force. Okay. So and it turns out that when two surfaces are in contact, they exert a force perpendicular to each other, and that's why it's called a normal force. Okay. So sort of what happened was, here are these atoms, these electron clouds repel each other, and then okay, so I don't know, maybe I shouldn't get into this, but now I'm already in it. All right, so there were the atoms before they came in contact, and the positive charge and the net electric charge were right on top of each other. So the atoms were neutral. And then when you bring them close together, what happens is the electron clouds repel each other. So now the electron clouds are there. The center of negative charge is there. The center of positive charge is there. Did you guys understand that? And now you see the positive charges see each other and they're repelling each other. Okay. So that's how the normal force comes about. Okay. That's how come you don't go into the earth, even though the earth is pulling you with a force of 160 pounds or whatever. Okay. All right. Anyway, so we will be dealing with this normal force. Okay. So again, it's called a normal force because it's perpendicular to the surface. All right, we'll go over this slowly because you'll use this in many problems. Okay. So what we'll be doing is the following. We'll put an object on a slope. Okay. And so we will need the following. Oops. Let go. Okay, I'm going to redraw this thing. Make sure you understand this. Okay, so there's the slope. The slope is given by that angle. And we'll represent this guy by a point. Okay. What is Earth doing to this guy? Pulling him down with a force equal to, there's the magnitude of the force. Okay. Now, so if let's say he's skiing and he's on a frictionless surface, this component of gravity is what is accelerating him that way. Okay. All right, we need to find that component. Okay. So this is theta. What is this angle? This is 90 degrees. So this is 90 minus theta. Okay. So what is this component equal to? It's mg cosine 90 minus theta. And cosine 90 minus theta is mg sine theta. Okay. What is this angle equal to? Theta. So this is mg, so this is mg cosine theta. All right, I'm going to redraw this. So what we are saying is the following. You put an object on an incline. Here is the force of gravity. And this component of gravity is mg sine theta. and this component of gravity is mg cosine theta. And these are the two most useful components. Okay. Why isn't this guy falling through the slope? Because the slope is exerting, the normal force of the slope is balancing that. Okay, so this is equal to that. So that's the normal force. And this force, this component of gravity makes him accelerate down. Okay. Everybody understand that? All right. So we'll use that quite a few times in solving problems. You almost want to memorize that. Okay. All right, you want to understand this term, tension. What does that mean? And this doesn't mean stress. Okay, so the best way to illustrate this is the following. Let's say you hold onto a rubber band and pull on either end with a 10-pound force. Okay, so you guys understand you can hold onto a rubber band and pull on with a force of 10 pounds. Okay, so what is this rubber band doing? Oops. If your hand is not moving, you're pulling with a 10-pound force, the rubber band is pulling you with a 10-pound force. And you're pulling here with a 10-pound force, the rubber band is pulling you with a 10-pound force. Okay, the rubber band is said to be under a tension of 10 pounds. Okay. So you can do that similarly with a rope. So if a rope is under a tension of 50 pounds, what does that mean? Whatever the rope is attached to, if this rope is under a tension of 50 pounds, the rope is attached to this guy, the rope is pulling this object with a force of 50 pounds. This rope is pulling this object with a force of 50 pounds. That's what that means. Okay? What's the direction in which the rope is pulling the objects? You can think of this as a rubber band. What does a rubber band want to do? It wants to shrink. Okay, so that tells you the direction of the force. All right, so you guys understand? Yep.
So technically, by this logic, tension is just force?
Tension is a force, yeah. Yeah. So all we're doing is we're introducing special kinds of forces. That's all. Again, various different. Because we are going to beat this equation to death. Okay. So tension is just. You guys understand? All right. So now you want to pay close attention to this. Okay. So you see in this diagram, the tension on this side of the rope is the same as this side of the rope. Okay, that is true only when this guy, the pulley, is massless and frictionless. Okay, so the tension in the rope is the same. Right now, for the money you paid, that's all we're going to deal with. When you pay a little more money, we'll make this massive. Okay, and still we won't deal with friction, but because that will be hard to quantify. And when when the mass of this is not negligible, then these tensions will be different.
Is that like physics 3?
No, not in physics. We let the engineers bother with that. Yeah. Well, yeah, okay. Anyway. All right, so every time you see a problem where the tension is the same, they won't state it, but it's implied that the pulley is massless and frictionless. Okay? Okay, any questions on that? Do you guys understand this? Okay, so now you understand if a string or a wire is under tension, what is it doing? It's trying to shrink, and it's pulling whatever it's attached to with that force. Okay, so if something is under the tension of 10,000 pounds, it's pulling whatever is attached to it with the force of 10,000 pounds. Yep.
How come in the diagram from before, if it's pulled from both sides with 10 pounds, It's
Mhm.
not 20 pounds, it's still 10 pounds.
Yeah. So this guy is not moving.
Okay.
This hand is pulling with a 10-pound force. So the rubber band is pulling in with a 10-pound force. The net force on that guy is 0.
Oh,
Okay. So the trick here is what you want to understand. This applies to everything. So this equation applies to this object. He's at rest. So the net force on him is 0. Okay. This is your right hand. Your right hand is at rest. So that applies to that as well. Okay. All right, once you learn all of this, here's what, okay, so you can learn to apply it to this kind of stuff. Okay, so here's the suspension bridge. Suspension bridge does the following. It doesn't like to switch applications. Come on. There you go. All right. Okay, so what's the difference between that bridge and this bridge?
Stack and fold up.
So, see, this bridge is made with a lot less material, and you can build this higher. Okay? So, how do we get away with this thing? Okay.
Stable because of the wire.
I'm sorry?
The wire is making
Right.
more stable.
Okay, yeah, so you will learn in chapter 12 or 13. Okay, so let's say here's what you learn. Let's say this could be a bone, a concrete column, or whatever. Okay, a lot of materials. Okay, let's say I apply 1,000-pound force in either direction. So this is a tensile force. Okay, I'm trying to stretch it. Okay. £1,000 force here. This is a compressive force. Okay. Will this break first or this break first?
Tense.
Hmm?
Tense. Aggressive.
Compressive will break first. Okay, it turns out this will break first. Most objects are much more strong under compressive forces. For concrete pillars, it's 10 times stronger under compressive forces than that. So what we are saying is, if 1,000-pound force breaks this way, you need 10,000 pounds to break this way. Okay. Did you guys understand that? So it's much stronger under compressive. And that is what's incorporated in this bridge.
Push it down.
So here's the deal. Let's say, okay, so we will, okay, so let's say you got to support 100,000-pound force. This is 100,000-pound weight. You got to support 100,000 pounds. And what we'll do is we'll suspend it with 100 wires, 100 cables. So each cable is bearing a force of 1,000 pounds. Okay? So each cable is under a tension of 1,000 pounds. This is pulling the road like that. This is pulling it down. And all these tensions get transferred like that. They're pulling down on this thicker cable. And they are pushing this guy down. What is this force without any calculation?
It's holding it down.
50,000 pounds. Okay, so you lifted 100,000 pounds using these tensions, which were 1,000 pounds each. So a smaller 1,000 pounds was distributed to the cables, a tensile force, and that was translated to a large compressive force. That's the idea of that, of the bridge. Okay. So you want your structures built such that the largest forces borne are compressive, and small forces, tensile forces, can be handed out to little minions. Okay? And that's the idea. So you built a large bridge with a big gap underneath with very little material.
So the tensile forces move up the cable, the top cable brings it down, the pillars are.
So this thing, this tensile forces, this is lifting this thing up and it's pulling down on that cable. And that cable is being pulled by by all these cables, and that's transferring this compressive force. Yeah. All right, so that's why you do physics classes, okay? To learn how to save money. Yeah. And you learn this over time. You guys know the Empire State Building, right? And you know the World Trade Centers. Apparently, okay, so if I remember my numbers right, if you used a 100-pound material there, you use 30 pounds here. All right, so you got that much better at construction. Apparently, the World Trade Centers were an acre floors, no pillars. All the pillars were on the sides. So it's like this. And here was the floor sitting on that. Yeah. All right. So we're talking about forces, and here are some forces. Okay, this is a DNA molecule, and to stretch a DNA molecule when you want to read it and make a protein, the force needed is 10 to the minus 15 newtons, and so on. Okay. I guess this is the weight of a guy, or maybe the force with which he kicks. Here, the force that the water is exerting on the dam. Okay, and so this is an arch dam which you can build if you're building on a canyon. So here's looking at it. So here's the force of the water, which is being, and so this is a compressive force, and which is being transferred to the canyon walls. Okay. Again, anytime you are to bear a large force, what does your design need to make sure? It's a compressive force. Okay. All right, so here are some simple machines. Okay, what is the point of this guy? What is the point of this guy? What does this guy do? Waste your...
The weight,
Huh?
organizing the weight with the wool on the wire.
Okay, so if you pull on this wire, you're lifting this weight. What is this guy doing? Why don't you lift it straight up with your hands? I'm sorry? You can't change its weight.
Take less force to lift it?
And that's right. Okay, so again, in the ideal case, if these are massless and frictionless, this tension is the same. So if this is a 100-pound weight, the tension is 50 pounds. Okay, so okay, you can lift this object up with a force equal to half its weight. Sounds like free lunch to me. What is the price you paid?
It's half the weight.
Complexity.
Yeah.
It moves half as far.
Very good, my friend. So to lift it 1 feet, you have to pull 2 feet. Okay. It turns out that work is force times distance. So work in is always equal to work out. That's in a frictionless system. Okay. So input force was half as much, but the input distance was twice as much. Okay. So this is called the mechanical advantage of a machine. Output force divided by input force. Okay. So if the input force was half as much, the mechanical advantage is 2. Yeah. Okay, so this, you just have to calculate how many strings are going up. So this has a mechanical advantage of 2. This guy, this setup has a mechanical advantage of 3. What does that mean? To lift a 100-pound force, you need to apply a force of 33 pounds. This setup has a mechanical advantage of 4. Okay. To lift a 100-pound object, you need a 25-pound force. Okay. All right, this is very important. We'll use this a lot. Okay, here's a mass attached to a spring. When you compress the spring, what the spring does is it pushes back on the mass. And if you stretch the spring pulls back. So this is the equilibrium position. If you disturb the system, the spring wants to bring back it to your equilibrium position. So the spring always applies a restoring force. Okay? And it turns out that the force that the spring applies is proportional to the displacement. The further out you are, the greater the force the spring will apply. Okay? So if x is positive, the force will be in the negative direction because of the negative sign. If x is negative, the force will be in the positive direction. If this is negative. Okay. K, so this is called Hooke's law. K is called the spring constant. And it tells you how stiff the spring is. Stiffer the spring, greater the spring constant. Greater the spring constant, greater the force it can apply for a given stretch. Okay? But the spring is always trying to bring you back to the equilibrium position. Okay? So that's why it's called a restoring force. So for instance, here's another. Okay, so in this case, if this is a valley, you take a marble, the gravitational force is a restoring force. Okay. If a marble is on top of a hill, the gravitational force is not a restoring force. It'll take you away from equilibrium. Okay. So here's an interesting pulley system. Okay. If M1 is greater than M2 plus M3, it'll accelerate downwards. If M2 plus M3 is greater than M1, it'll accelerate up. Okay? All right. So if these are heavier, then this will go up. Okay? Everybody understand that? So here's a very interesting thing you can build with it, this idea. So here are 4 buckets. If those guys are heavier than the table will want to go up. So the tension in the string is pulling it up. And you don't have to nail them down. In fact, if you want to sit on that, you can sit on that. You just have to make sure that the weight, the sand in this thing weighs more than you and the table. And you can sit on that. Okay. All right. You need to have heard this term, okay? What are Newton's three laws? First law says if force equal to zero, acceleration is zero. Second law tells you force, and the third law says action and reaction are equal and opposite, okay? All right, it turns out that Newton's laws apply in inertial frames. So inertial frames are non-accelerating frames. A non-inertial frame is an accelerating frame. Okay? So what is a non-accelerating frame? So if something is moving at constant velocity, it's non-accelerating. Okay? So what does Newton's law say? The first law says if the net force acting on an object is zero, its acceleration is zero, and it will move in a straight line. Okay? It will maintain constant velocity. Okay, now let's do the following. So a non-inertial frame is a accelerating frame. So for instance, a rotating frame is an accelerating frame. It's a non-inertial frame. If you're standing on a merry-go-round and it's spinning, that's a rotating frame, and that's a non-inertial frame. Okay? So in physics, we do a lot of thought experiments. So let's do one of this thought experiment. Okay, so let's say you're Santa Claus and you're playing hockey. You hit a puck. Okay? You hit it on ice, that's frictionless. Okay? And let's say you're hovering in space. If you're hovering in space, you see the puck traveling in a straight line. But if you're a polar bear and you're standing there and watching it, this is the trajectory you see. Okay, again, we're at the North Pole. You hit a puck like this, okay? And if you're standing there, the Earth rotates and the puck goes to the right.
Is that like the Coriolis effect?
All right, just a second. All right, so here, there was no force acting on this guy, and it's not traveling in a straight line. Well, Newton was all wrong. Well, Newton wasn't wrong. I mean, Newton's laws apply in inertial frame. Well, you were looking at it on a non-inertial frame, and that's why you had to explain this, you had to invent a fictitious force. Okay? You're saying, oh, there must be a force acting on it, that's why it curved. And that's a Coriolis force is a fictitious force. Okay. So when you try and apply Newton's laws from a non-inertial frame, you have to come up with a fictitious force to explain things. Okay. All right. So that covers chapter 5. I hope I didn't go too fast. So